Good morning, everybody. Today we're going to learn about how to use electronegativity to predict which kind of bond a molecule is going to form. There's 4 different kinds of bonds we're going to talk about in this class. There are ionic. In ionic bonds, electrons are completely transferred between one atom and another. They're taken, not shared, just like the joke I showed you the other day. Polar covalent bonds. The electrons are shared, but not equally. So one of the atoms is sharing, but it's not being fair. It's holding on to the electrons more tightly than any of the others. So the electrons are spending more time near that one particular atom. Non-polar covalent bonds, the electrons are being shared equally. So they're going to be almost equidistant, almost equal, almost midway between 2 different atoms. And then finally we have metallic bonds. With metallic bonds, we have nuclei of the metallic elements, and they're sort of swimming in a pool of electrons. And I've tried to explain this to people as if we were all swimming in a public pool. I don't have my water and you have your water and our waters don't touch. We're all just kind of moving around inside the same water. That's why we want you to take showers before you get in the pool. All right, so let's use electronegativity to try to figure out or predict which kinds of bonds that different molecules are going to form. So the first one that I'm going to look at is, let's look at bronze. It's a very important compound or mixture historically. Bronze is made of, I'm going to erase these. Bronze is made of a mixture of copper and tin. Well, before we go any further, these are both metals. Metals are going to form metallic bonds. So when I have copper and tin, that's going to form a metallic bond. And I'm not going to move on any further. I don't have to do anything else. Let's look at another one. Let's look at, say, diatomic hydrogen. And just in case you haven't run into that term before, di just means 2. So diatomic means there's 2 atoms. That's all. Diatomic hydrogen. It gets lonely. It likes to hold hands with another hydrogen atom. So we have H2. We're going to look up the electronegativity on a chart or a table. You are not expected to memorize these things. When we look it up, we find out that hydrogen has an electronegativity of 2.1. Well, the other hydrogen is going to have an electronegativity of 2.1. So that means the difference between them is 0. When we have an electronegativity difference of 0, that is going to be a non-polar covalent bond. They are sharing exactly equally. So non-polar covalent bonds have an electronegativity difference of between 0 and 0.5. So that would include our diatomic hydrogen. Polar covalent bonds have an electronegativity difference of somewhere between 0.6, and in this class we're going to make the cutoff at about 2.0. Different people argue about where the cutoff is. In this class, these are the numbers we're going to use. If the electronegativity difference is higher than 2.0, then it's going to be an ionic bond. So let's go ahead and look at another one. Let's look at silicon dioxide. So here is silicon dioxide. I'm going to look up the electronegativity of silicon. You can't see it, but I have it being projected on my screen right now. That is 1.8. I'm going to look up the electronegativity of oxygen. That is 3.5. So I have 3.5 minus 1.8. That is an electronegativity difference of 1.7. That puts us firmly into the polar covalent bond. So silicon dioxide is a polar covalent bond. Diatomic hydrogen is a nonpolar covalent bond. It has an electronegativity difference of 0. And I'm going to have to finish this up quickly before people come into class. Okay, the last thing we're going to take a look at is potassium chloride. So, potassium has an electronegativity of 0.8. Chlorine has an electronegativity of 3.0. So that's an electronegativity difference of 2.2. That's greater than 2.0. So we know that potassium chloride is an ionic bond. I hope that helps you.